Okay, so where we left off before our little break, we were talking about what happens in a titration when we have a strong acid and a strong base. So now we're going to talk about what happens when we have one of them is strong and one of them is weak. Okay, weak acids and bases, just as a reminder, do not ionize completely in the solution, right? So we have an acid here, and you can see the equilibrium arrow, right? So whenever something does not happen completely, this is an equilibrium problem. And you should expect a double arrow somewhere in your question. So this would seem to indicate that weak acids and bases do not neutralize strong acids or bases very well. This is not 100%. This is 100% not true. Okay. Weak acids and bases can neutralize strong acids and bases as if they were strong. So it says, if we recall Le Chatelier's principle, we can see why this is. Okay, so let's talk about this. So we'll take a weak acid and we'll put it into a solution with water. So that weak acid will ionize and it will become H3O plus and A minus, right? So the H joins the water and it becomes H3O plus. So we have an acid, and water will be acting as the base here. It will accept a proton, right? Bases are proton acceptors. So it will make H3O plus, which is the conjugate acid. Yeah, I can finish this. Conjugate acid, and then A minus would be the conjugate base. Okay, so this won't happen all the way. You can see the equilibrium arrow, right? Something is going to stop it from ionizing completely. But then what's going to happen is if we add a base, we can look down here as to what happens. When we have a base, the H3O plus and the OH minus will react to form water. Okay, when the H3O plus reacts and forms water, what's going to happen is it's like removing a product from this equilibrium equation, right? And when we remove a product, remember the equilibrium shifts to the left. No, sorry, to the right. A little sleepy today. I forgot my left from my right. Okay, so when we remove the H3O plus by reacting it with OH minus to form water, it's like removing it from the solution. So when we remove it, Le Chatelier says that what's going to happen is more reactants will react, right? More reactants will react to relieve the stress of the missing. Oh, it doesn't work. The missing product. Right. So when we remove a product, we throw the equilibrium sort of out of balance, right? And the reactants will react to help us recover the H3O plus that's being taken away. So if we add a strong base to a weak acid, okay, strong base, weak acid, right? We are going to get an equilibrium situation, okay? And the product side is going to disappear, and that's going to keep shifting everything towards the right. So it says, looking at the product side, we can see the hydronium ion. Remember the hydronium H3O plus and a hydroxide ion, OH minus, will react with one another to form water. Okay, this means that our weak acid that in our weak acid equilibrium, we are removing product. As Le Chatelier's principle predicts, the equilibrium will shift to the right in response. In other words, more acid will dissociate, right? Dissociate is a word that means to break up into ions to make up for the lost hydronium ion. As a strong base is added, the weak acid equilibrium will continue to dissociate until it is all used up. Right? So the weak acid dissociation becomes quantitative. We will use it all up. Okay, it will all dissociate. Okay, thus weak acids and bases can neutralize as if they were a strong acid or a strong base, because when the H3O plus and the OH minus, they react to form water, it's like pulling them out of the equation. So we're always going to shift that reaction to the right until everything is used up. So this is good news because we can use some of the same math as we used in the last section, okay? But that's not the end of the story. So all of the acid gets used up, but when all the weak acid has been dissociated to neutralize the base, all we are left with is water and a conjugate base, okay? So you can see we will have the H2O, right? And the H2O comes from H3O plus and OH minus, right? They become H2O, right? So that's where that came from. So all we're left with is water and the anion of the weak acid. Right? Which, if we're looking, right? We're looking, sorry, back up here, right? That's the conjugate base. Okay, so we're left with a conjugate base. And this will result in an endpoint that is mildly basic. So it says the resulting neutralization, because everything is either water or conjugate base, okay, we're going to get a solution that is very mildly basic. The reverse occurs with the titration of a weak base. So if you titrate a weak acid, it's going to be mildly, with a strong base, it'll be mildly basic. If you titrate a weak base with a strong acid, the resulting solution will be mildly acidic. A popular acid-base titration question is to ask what the pH is after the titration of a weak acid or base. So let's take a look at how to solve this problem. Okay, so it says a solution of acetic acid of unknown concentration. So we have acetic acid, right, which is HC2 H3O O2, I think. I took a lot of biology, so I'm used to seeing it more like this. Two C's, yes. Okay, we're good. All right, so acetic acid is this. You can see it's an organic acid because it's only CH and O atoms. And so it's going to be weak. Okay. Because remember, our strong ones are like H plus group 17 elements, or H with SO4, or H with NO3, or H with ClO3. And acetic acid is not on that list. Okay. It's of unknown concentration, which means it's going to be the analyte, is titrated by 0.15 moles per liter of KOH, right? So is titrated by means that KOH is the titrant, and it is a strong base. So we're titrating an unknown weak acid with a known strong base. It says if it takes 35 milliliters of potassium hydroxide to neutralize 20 milliliters of acetic acid, determine the concentration of acetic acid and the pH of the resulting solution. Okay, and it tells us the Ka of the weak acid. So the thing about weak acids and bases is they'll have a Ka, right? And we're going to need this because we're going to have a little bit of an equilibrium problem at the end. So let's take a look at how to solve this. It is, I believe, solved on the next page in steps. So the solution says the first part of the solution can be determined exactly the same way as we calculated the concentration in the strong acid versus the strong base titration. So we know that when they're neutralized, the moles of acid and the moles of base will be the same, right? So we can use the C acid times V acid equals C base times V base equation. Here, it has been rearranged so that we can solve for the concentration of the acid. Okay, you can rearrange the equation either before you put in any numbers, but a lot of people are more comfortable putting in the numbers first and then rearranging, because I find it's a little bit easier for brains to like process whether a number is multiplied or divided, then process whether a letter is multiplied or divided for some reason, right? Our brain is meant to handle real life numbers and not these symbols. Okay, so we fill in the numbers, we rearrange the equation, and we find the concentration of the acid is 0.2625, but we're going to use two significant digits. Why? Because our lowest, we have two significant digits in the 0.15 number, right? There's three significant digits in the 35.0, and there's three significant digits in the 20.0, but there's only two significant digits in the 0.15. So that means that the acid, there's about 0.26 moles per liter, right? It has a very low concentration. Now, if we want to, so that part is exactly the same as we've done before. Now, if we want to calculate the pH of the resulting titrated solution, that's where things get a little bit different, okay? So for strong acids and strong bases, we know automatically, boom, the equivalence point is going to be at 7 because they completely neutralize each other, okay? They're equally as strong. But here we have a weak base, sorry, a weak acid and a strong base. So we should expect that the equivalence point is at a higher pH. It's going to be slightly basic. So it says we should expect an answer that gives a pH of slightly higher than 7. right? Because our base is strong and our acid is weak. We know this because only the Bronsted-Lowry species left in the solution will be the conjugate base of the weak acid. So the solution should contain hydroxide ions. Okay, so if you have the conjugate base, like we did back here, right, and it reacts with water, we get OH minus ions as the conjugate base. The conjugate base of A minus, right? So the conjugate base becomes the regular base of this equation. The water will become an acid. The OH minus will become the conjugate base of H2O, and HA will become the conjugate acid, right? So we're using this. So the solution will contain hydroxide ions. To begin, we need to determine how many moles of conjugate base have formed. Okay, so what we're going to do is we're going to use this number from the previous calculation, and we're gonna this is the volume of the solution. Right, so if we, sorry, to go back again, okay, that's right here. Right, so it's the concentration times the volume of the acid, right? So we can get those from the previous question, okay? And we find out that there are 5.25 times 10 to the negative 3 moles of acid to start out with, okay? Then, okay, the concentration of the conjugate base, so this number here that I said is the volume of solution, I should say is the volume of the acid, okay? You're going to take the volume of the acid and the moles of the acid and the concentration of the acid and the volume, there we go, of the acid, it's even written there, from the first equation, and we're going to use that to calculate the moles, okay? And then the next step that we're going to do is, because we added an acid to a base, right? Once we've added them together, it's going to have a higher volume, right? So the total volume is the volume of the acid plus the volume of the base, right? When we added the acid to the base to neutralize it, right, we had 20 milliliters of acid and 35 milliliters of base, right? So the total is, when we add them together, is we just have to add those two numbers. So we're going to end up getting like 55 milliliters total of liquid. Okay, so the concentration of the base, we take the moles from our last calculation and we divide it by the volumes of the acid and base added together, and we're going to get the concentration of the base, which is this, right? So yeah.
Where did you get the 5.25 times 10 to the power of negative 3?
We multiplied. So in the first step, our goal was to find the concentration of the acid, right? C acid, right? So this 0.25 came from the previous calculation. This is the volume of the acid here that came from the question. And when you multiply concentration by volume, you get moles, right? So this is the moles of the conjugate base. So it's A minus, right? So I took that calculation and that number, that 5.25 times 10 to negative 3 goes into finding the concentration of this base. So the moles comes from that calculation, and the volume comes from adding the acid and base volumes together, right? And then we get this concentration of a base here. So whatever you calculate here is the amount of this that we start with. Okay, so let's just, the first thing that you do is you have to find the concentration of the acid, and you use the C acid times V acid equals C base times V base. We find the concentration of the acid. Okay, then we need to go from the concentration of the acid to the moles of the acid, right? So we ended the first part with the concentration of the acid, but then we needed to find the number of moles of the acid, because all of those are going to turn into the moles of the conjugate base. Okay, and we need the conjugate base to determine the pH, right? So the moles of the acid, right? C acid times V acid gives us this number. And then we have to divide it by the total volume of the acid and the base together, because we mix them, right? And then we divide and we get this number, and this number is what we start with here. Now, this is bad because this is starting to look like an ice table. And that's exactly what we're going to do to determine the pH. So once you find out how much conjugate base there is, okay, you're going to go down and you're going to set up your ice table. So you can see here I have the ice table, and A starts with 0.9545. O and HA start with 0. Okay, so this is what's left of our initial weak acid, right? It will change, it will decrease over time, and OH and HA will increase, right? So now we can use our KB for the conjugate base, and we can set up using the equilibrium expression. So this X comes from here. This X is this X. And this becomes this. So we have our KB expression, and this setup here. So it says at this point, you may notice in the question we're given the Ka of acetic acid, but not the Kb of the acetate ion, right? So we used acetic acid, and acetic acid is really easy to find the K value in a book, right? And we've used it a lot in this unit. So I don't know if you've memorized it at 1.8 times 10 to the negative 5, but I sure have. Okay, but that's not the value that we can put here. That's not a number that we can put in here, because this is Ka and this is Kb, right? So we need to find Kb first so we can substitute it in and solve. So we're going to use this equation. Remember that Kw is equal to Ka times Kb. We know Kw because it's a constant. We know Ka because they gave it to us, and we can use it to find Kb. So Kb is Kw over Ka. Kw is 1.0 times 10 to the negative 14. It's a constant. It'll always be that. And Ka is 1.8 times 10 to the negative 5. Okay, so we divide them. We get the Kb. Now, we put the Kb into the equilibrium expression. And now we have a number for that as well. Okay, this is starting to look bad because we can't use the perfect square rule, because the bottom is not a perfect square. X is to the power of 1. Okay, so we're going to try another little trick. This is a weak acid, so that means it's Ka and Kb are all small numbers, right? KB is times 10 to the negative 10. This is very small. And when your K is very small, there's a very good chance that the 100 rule will work. So we take our initial concentration, right? This is the initial concentration of our base. And we divide by KB. And we find out that it is much bigger than 100. Okay, so what is that? 0.09545 divided by 1.8. Times 10 to the, oh, it's negative 10. Crap. Okay, let me try that again. 0.95, oh, 0.09545 divided by bracket 1.8 times 10 to the power of 10. I did it wrong again. 0.09545 divided by 5.556 times 10 to the negative 10 is a really, really big number. Okay, way bigger than 100. Do it on your calculator. I was gonna try to read it out, but it's just a very big number. Okay, so therefore, since the 100 rule is confirmed, we can say that any x's that are added or subtracted, we can get rid of. So this x here in the denominator, right, is added or subtracted. So we can get rid of it because of the 100 rule. Okay, so you can see that 0.09545 is going to become minus x is going to become 0.9545. We're just going to get rid of the x's that are added or subtracted. So we go from that number minus x to just that number. So what we can do is we can cross multiply the 0.09545, right, with the 5.56 times 10 to the negative 10. We get this number. Okay, we need to square root both sides because we don't want x squared, we want x. And we end up with 7.282 times 10 to the negative 6, which is x. Okay, that x is equal to the concentration of hydroxyl ions, right? So the concentration of hydroxyl ions is that number that we just calculated. We can use the concentration of hydroxyl ions to find the pOH, right? We just take the negative log of it, and then we find that the pOH is 5.138, and the pOH is 5.138. So we can calculate the pH by doing 14 minus the pOH, and that'll give us a pH of 8.86, at which we're going to stop and think about it, whether this is appropriate or not. So we have, right, a weak acid plus a strong base, and that should be slightly basic from our notes, which means in terms of numbers, it should be above 7. Right? If it's below 7, you know you've done something wrong. Usually, people get to this step and they do everything right until they get to this step. And then instead of calculating pOH, because it's the same as the OH minus, they will calculate pH, right? And then it'll be too low. The pH will be like 5, right? So it'll look acidic, and then it's very stressful. So our answer works out. The pH of the final solution is 8.86. So we would need to find an indicator, right? If we were doing this titration, right? Our indicator needs to change color around 8.5 to pH of 8.5 to 9.5, right? We need it to change color around there. So if you have a weak acid and a strong base, we'd have to choose a different indicator. We couldn't use one of the indicators that changes color at 7, like bromethymol blue from the gizmo. How does it affect the titration curves? Well, if we start off with a strong base and this is how would the titration look for a titration between a strong and a weak acid base? Oh no, something happened here. I don't really like the wording. But it's okay because we have two graphs. The first graph shows us a strong acid into a weak base. So the weak base, because it's a base, right? So this is the titrant, and this is the analyte. Okay, because our analyte is a base, it'll start off above 7, but because it's not a strong base, it'll start off below 14. So a strong base starts off right at 14, and a weaker base will start off somewhere between 14 and 7. Okay, so you can look at the beginning point to determine whether a strong base or a weak base was a part of the titration. Okay, then sort of everything will happen the same. So the pH will fall pretty steadily until it gets to around the equivalence point. At the equivalence point, there will be a very quick change in pH. And you can see the equivalence point if you have a weak base is acidic. So before this, the last question we did, we had a weak acid, right? So the equivalence point here has to be less than between 0 and 7. Okay, so if you have a weak base, you're going to have an acidic equivalence point, and you're going to start off in the basic range, but not at 14. You're going to start off lower than 14. And your equivalence point will be slightly acidic. If you do the opposite, so here it shows running a weak base into a strong acid. So the acid here is our analyte, and the weak base is our titrant. So you always start off with the analyte, okay? The analyte is the strong acid. So the thing that is running is always the titrant, right? So because we're starting off with a strong acid, we start off at a pH of 0 because strong acids have a pH of 0. And then we are going to move up, and because we're using a strong acid, weak base, the equivalence point is going to be acidic, right? So whatever is weak in your titration, whether it's the analyte or the titrant, right? So here in situations 1 and 2, right, the weak thing is the base, okay? And if you have a weak base, that controls the equivalence point. So if the base is weak, you're going to have an acidic equivalence point, whether that's the titrant or the analyte. The analyte determines where we start. So a strong acid starts at 0. a weak acid would like start less than 0, or sorry, more than 0, less than 7, right? If you have a weak base to start as your analyte, it would start less than 14, somewhere in there. It doesn't have to be exactly there, just somewhere that's lower than 14. And if you start with a strong base, you're going to start at exactly pH 14, right? So the analyte determines where at each of these 4 places we start, okay? The weak thing, okay, whether it's the analyte or the titrant, the weak thing determines where the equivalence point is. Okay, so the analyte, whether it's an acid or a base or strong or weak, right? That determines where the line starts. Okay, whatever is weak determines where the equivalence point is. So this says at the beginning of this titration, you have excess hydrochloric acid. The shape of the curve will be the same as when you had excess acid at the start of the titration running sodium hydroxide. Basically, if it is a strong acid, it always starts at 0. It's only after the equivalence point that things become very different. It says a buffer solution is formed containing excess ammonia and ammonium chloride. We'll talk about buffer solutions in a second. This resists any large increase in pH, and you would not expect a very large increase anyway because ammonia is a weak base. Right, so studying the titration curve will let you figure out what your titrant was, what your analyte was, and whether it was strong or it was weak. So buffer solutions, and this is the last thing that we're learning in equilibrium. If you are going into a medical type field, you need to understand buffer solutions because our body only works at a certain pH, and it's a very, very, very small window, especially for your blood. Your blood needs to be at a pH of around 7.35. So you might be able to go up to 7.45. You might be able to go down to 7.25. But if the pH differs any more than that, what happens is all of the proteins in your body that are responsible for all the jobs of keeping you alive, they change shape, they stop working, and your body stops functioning, and you die. So it says a shift in either direction by more than 0.15 can be fatal. So blood pH is one of those things that is monitored very carefully in patients who have certain conditions, especially probably the most important organ for keeping the pH of your blood constant is your kidney, right? So if your kidneys go, and if you've watched like whatever, however many, 17, 18, 19 seasons of Grey's Anatomy, or you're binging it right now, watch what happens to people who have kidney problems and need kidney surgery. Most of the time they die, right? So you'll hear on like medical shows, oh, the patient is going into renal failure, and they're going to be dead. And that's because the kidneys, right? Renal means kidneys, are responsible for keeping your blood in check, pH wise. Okay, so buffer solutions are special acid base equilibrium systems. In a buffer solution, there is a resistance to drastic change in pH, even when strong acids or strong bases are added. So we have a buffer solution. Our blood is a buffer solution, right? Our blood is designed, the chemicals in our blood are designed to keep it at 7.35. And you may notice that if you interact with a lot of medications, a lot of our painkillers are also buffered, right? They're buffered because they don't want to mess with the pH of our stomach, right? So a lot of people, when they take a lot of painkillers, their stomach gets too acidic and messed up, and it can result in ulcers and things like that. So that's another situation in the medical field where having something be buffered is very important, because we want our stomach to be acidic, but not too acidic. We want our blood to be slightly basic and not change from 7.35 to make our body work. Okay. So buffers are vital to biological studies of foods, soils, molecular biology, and cell biology, as well as clinical trials of pharmaceuticals. Okay. So if you're planning on doing anything medical, this is something that you will study a lot in your undergraduate degree. Okay, so buffers. A buffer is usually two solutes working together to keep the pH at the same level. One is a weak acid, and the other is its conjugate base. So we're going to get a salt that contains the conjugate base, and we're going to use that together with the acid. So for example, if we chose acetic acid as our acid, we would choose, this is sodium acetate, as our conjugate base. So basically what would happen is we take the H off the acid, right? And we replace it with like a group 1 metal. We're gonna say like maybe sodium is the best choice for that. A lot of our medicines are sodium something. Okay, carbonic acid is another weak acid, right? That's H2CO3. Okay, and its conjugate base, we've taken one of the H's. So we start with 2 H's. We've taken one of the H's away. There's now only one H. And we've replaced the H that we've taken away with a sodium, right? So now we only have one H, and what's taken place of the other sodium is an Na. Ammonium chloride is, ammonia is a weak base. And ammonium chloride is its acid conjugate. So what happens in its acid conjugate is we've added an H, and we've added a group 17 element, which is usually chlorine. So the first two are examples of weak acids and their conjugate bases. The last one is an example of a weak base and its conjugate acid salt. Okay, so when you go from a weak acid to its conjugate base, you just remove the H and add an Na. When you are going from a weak base to its conjugate acid, you would add, instead of removing an H, and then you would add a group 17 element. Buffers don't keep things neutral. They just keep them within the same range. That's important to note. So buffers won't keep things at 7. Buffers can be designed to keep the pH at basically any pH you want. You just have to find the right acid or base and the right conjugate. So often a buffer will be used at a specific pH that may be anywhere in the pH range. Buffers also have a capacity that can be surpassed. So the capacity of the buffer is also important. So this buffer solution, depending on how much acid and how much salt we have, right, can prevent a big pH change until the buffer components are used up, right? So it won't work indefinitely, but it will work for a long time, okay? To keep the pH the same. Eventually, you're going to use up one of your buffer molecules, and the pH after that will increase or decrease, depends. Type 1 buffers. So type 1 buffers, we have different types of buffers. Type 1 buffer is a weak acid and its conjugate base, right? HA is what we use to show that we have a weak acid, and A minus is the conjugate base. Both key species are determined in the ionization of the acid. So when we ionize the acid, we get the conjugate base. Okay, so both of them are present in the same equation. Okay, both of these are going to be weak. The acid is going to be weak. The conjugate base is going to be weak. So what happens? Why does the solution keep at the same pH? If we add an acid, okay, what's going to happen? If we add an acid, what's going to happen? So what's going to happen, right? We're going to make more hydronium. Okay, so we're adding H3O plus. Okay, so if we make more H3O plus, if this increases, okay, remember, according to Le Chatelier's principle, that's LCP, okay, if we increase this, this creates a stress, and the equilibrium will shift to the other side to get rid of some of the H3O plus. So what do we end up making? A weak acid. Okay, so basically, if we add a strong acid, the buffer solution turns it into a weak acid. Okay, if we add a base, what will happen? If we add a base, it's going to use up the H3O plus, because the OH minus is going to react with the H3O plus, and it is going to remove some of the H3O plus from the system. Okay, so this decreases, and now we're shifting to the right, right? Due to Le Chatelier's principle. If we remove a product, the system will make more product. And then what are we going to get? We're going to get a weak conjugate acid and water. So if you add a strong base to this, if we add a strong base, it will result in a weak base and water, right? So this resists pH change in both directions. It will use up a strong base, and it will use up a strong acid. So thus, one member of the buffer team will neutralize any strong acid, and the other member will neutralize any strong base. Isn't that cool? So it turns strong acids into weak acids and strong bases into weak bases. In our blood, the buffer system that we use is a weak acid called carbonic acid, right? So when you have carbon dioxide in your blood, it will turn into carbonic acid, which is a very weak acid. It's the same acid in like soda, in pop. Um, and its conjugate base is something called bicarbonate, HCO3 minus, right? And so in order to keep your blood at about 7.35, it will use up either bicarbonate if we add too much acid to your blood, or it will use up, sorry, is that right? I think so. Or if you add a strong base, it will use up the carbonic acid. It says, consider that the soluble salt will ionize 100%. Okay, so we had a problem here. Maybe not. Consider that soluble salt will ionize 100%. Thus, we can turn A minus. Recall the definition is this. Molar concentrations can only be considered at equilibrium. Okay, listen. If you have a buffer solution, always easier to explain this with a word problem. If we have a buffer solution and we have to determine the pH of it, okay, so it gives us here, this is a salt and a weak acid. Right, and then we have the concentration of both. What is the pH of the solution? Okay, so we know also the Ka of acetic acid is 1.8 times 10 to negative 5. We know the concentration of the acid is 0.090 moles per liter, and the concentration of the anion or salt is 0.11 moles per liter. The traditional way to do this is at equilibrium, right? So we make the equilibrium expression, Ka equals, maybe we should show you no, the equilibrium reaction is this, Ha plus H2O, weird arrows. Oh, that was a horrible, pretend those look like equilibrium arrows. Makes H3O plus and A minus, right? So that's our equilibrium equation, right? So the equilibrium expression here is going to be the products, which is H3O plus or H plus and A minus, right? So the concentration of these two things over the concentration of the reactant, right? And we would use the acid, but not water. Water never gets used in these things. Okay, so we can rearrange this to solve for the H plus, the concentration of H plus ions, because we have, right, this is A minus, and this is HA. Okay, so if we rearrange the equation, we have HA is equal to Ka the concentration of H plus is equal to Ka times HA divided by A minus. And then we just substitute in. We know that Ka is 1.8 times 10 to the negative 5. We know that HA is... What did I mess up here? Either I messed up the substitution or I messed up the... Yes, I did. Okay, so I messed up the rearrangement. Okay, if we're trying to isolate this, H plus, okay, let's do a little math over here. I'll get my pen out. And we can talk about the mistake that I made. Here's the equilibrium expression. Ka equals H3O plus, I can use H3O plus because we have it here, times A minus all over HA. Okay, we want to isolate H3O plus, right? We want to isolate this guy. Okay, so we need to move the two things that are on the same side of the equation as H3O plus. So this one is multiplied, right? And we need to move it to the other side. Okay, so and this one is divided, right? So when they change sides, okay, the multiplication one on the A minus is multiplied, right? It's going to be divided. Okay, the oh, sorry, I messed up. Hold on. Divided. Okay. And then this HA that was divided on the other side, it will be multiplied. And then we have H3O plus is isolated. It's on its own. So my rearrangement in the notes was bad and it needs to be fixed. Okay. So now we substitute. So for Ka, we substituted 1.8 times 10 to the negative 5. Okay. For HA, we have to switch this. 1.8 times 10 to the negative 5 times 0.090, right? Because that's the concentration of the acid, divided by 0.11, which is the concentration of the conjugate base or the anion. Let's put that into our calculators and we'll see if magic does not happen. So yes, okay. So if you do this in your calculator, you should get that. And if we do the negative log of it, we get 4.82. I gotta write down somewhere that we have to fix this. Okay, that's how we would do it normally with our skills that we learned in this unit. In university, you will learn about the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is a shortcut. So if we know the pKa of the acid and the concentration of the anion and the concentration of the acid, we could find this. To get the pKa, you take the negative log of the Ka, and then you would do 0.11, which is the concentration of the anion, divided by 0.090, which is the concentration of the acid. You would multiply those first. You would take the log of it, then you would add those two numbers together, and you would still get 4.82. This is considered a shortcut, but I don't see how, right? It all depends what information is given to you and what you feel most comfortable with mathematically. If you're like me and you have problems rearranging equations, I can't believe I rearranged that equation wrong, then maybe try the Henderson-Hasselbalch equation. But you can do it either way, and it's about the same amount of work. So we have some practice questions here if you want to practice with buffers. Okay. And we have the answers at the bottom, so you can try those out. I definitely won't be giving out a buffer question on the exam. Or maybe I will, because the weak acid base one is a little bit crazy too. We'll see. I have to check over the exam. We'll try to keep the calculations to a minimum on the exam. So definitely a strong acid-base titration would be something that I would give off on the exam. Maybe not a weak acid-base titration. The buffer one seems pretty simple, but I'm not likely to give you it because I messed up a little bit on the note here. Okay, your assignment today. I just added it this morning, is a titration lab. Understanding titration is a good thing because if you're going off to university, because it is one of the most common labs in first year chemistry and in last year of high school. So I want you to have some idea of how it works. Okay. I have uploaded a document that you can type in, a PDF that if you want to write on, if some people have note-taking programs and they can physically write on PDFs on their like tablets, that's fine. Either one of these. So this is a gizmo. So you're going to go to gizmos, and you can see it's on our class gizmo list. So it's a little ways down. It's third from the bottom. You can see this titration. Okay. So you're going to do a virtual titration. It's going to ask you what you remember about acids, bases, neutral substances, right? And litmus paper, so you can see it there. Make sure you pull it up in color. If you print it off, it might be in black and white, and you might not be able to do this question. So make sure you look at the litmus paper in color. And then it shows you how to operate the titration. So there's a gizmo warm-up, right? And it will show you how to select what's in the burette, that's your titrant, and what is in your flask, which is your unknown, your analyte, right? And it's gonna show you that we have lots of different indicators. So in this lab, okay, we have a whole bunch of different titrants. Okay, they're all strong. We have some analytes, some are strong, some are weak. And we have some indicators. And when you change the indicators, it will show you their range. Okay, so bromethymol blue is yellow below 6 and blue above 7.6. Methyl orange is red at below 3.1 and yellow above 4.4. Phenolphthalein is colorless below 8.2 and pink above 8.2. So if you think about it, bromethymol blue is a good indicator for things that will be neutral when you mix them. So like a strong base, strong acid, right? Where you have a pH at equivalent 0.7, right? So here we have NaOH, HBr. that gives us an equivalence point of 7. So bromothymol blue is perfect because 7 is right in between 6.0 and 7.6. But say you change it from a strong acid to a weak acid, you can see that the equivalence point is 9, right? So we don't want to use bromothymol blue. We want to use the indicator where the pH is similar to the equivalence point. And this is as good as it gets for the 3 that we have. If you have a strong acid and a weak base, right, the equivalence point is lower than 7, so we would use methyl orange instead. Okay, so there you have your setup. As you release the titrant, the thing in here, okay, you'll notice that the volume, I couldn't think of the word for volume. I need coffee. The volume will go up, right? So you'll have a final volume when this all changes color, right? So this has changed color. And I use 9.9 milliliters. You have a worksheet that will allow you to determine the concentration. It's the lab will walk you through this, but see how it says moles of NH3 here, right? You would determine that from the balanced chemical equation. Okay, so I have 2 moles of NH3 in the balanced chemical equation. So I would put at the top 2. And then it says moles of H2SO4. I don't have anything in front of H2SO4. So that's 1 mole. And then the millimeters of H2SO4, that's what's in my burette. So that would be 9.9, right? The milliliters of NH3 are is right there in the flask, 100 mils. And then it says the moles per liter of H2SO4. You can see it's 0.80 molars. Right? So all you have to do, right? You don't have to think too hard because this has arranged everything for you. All you have to do is use the calculator and you should come up with the correct solution. Or sorry, the correct concentration. So, I didn't do a great job on this, so I definitely wouldn't like screenshot this and think you got the answer, right? You have to make sure that you do this very carefully so that as soon as it turns red, you stop the acid, the whatever's in the burette from coming in. If you wait a little bit too long, you might get the wrong answer. So the concentration of this unknown flask of ammonia is 0.158 moles per liter, right? And then let's check to see how well I did. It says I have the incorrect volume of titrants. And you know why? Because I had this on high, right? So the idea is here that you have to be very careful. So as soon as it starts flashing red, you can put it on high, but once it starts flashing red, you got to put it to low, right? And then you got to sit there and you got to put your cursor and on the stopcock and wait for it to turn all the way red and then stop it right away. Come on, turn red, there. Okay, so it turned red and right away. And now I only have 9.3 mils. So let's see if this, so you can check, which is great. Oh, so this is moles, sorry. Moles of NH3 is 2, moles of this is 1, mils of H2SO4 is 9.3, mils of ammonia is 100, the concentration is 0.80, right? Calculate, now I have 0.149. I check, great job, right? So the way you perform this lab is going to indicate whether you get the answer right or the answer wrong. You have to make sure that as soon as it turns red, you stop any of the titrant from going down. And even like I thought I was good, but I went over by 0.02 moles per liter. So I was close, but I was not perfect. Okay, so definitely the attention that you pay to this lab is going to determine whether you get the answer right or wrong, but you can always hit the check button to see how far off you were. Okay, so download this. It's a little bit of a lengthy lab. It's, I think, 7 pages, right? It's got some graphs for you. It's got some math for you. It's got some thinking about what's going on for you. But if you do this lab, you should understand titrations really well. So that's your homework. That's assignment 10. It's due, today is Thursday, Friday, Monday, Tuesday at midnight. Again, if you're falling behind, no worries. Just, let me know if you're not going to finish this on time, and then we'll give you a couple extra days to do it. So that's it for today. You have your homework. Have a lovely day, and we'll see you tomorrow.
Bye, Miss.